Alright, class, welcome back to my YouTube channel. We're doing some more mechanism and synthesis problems for your exam tomorrow. We're feeling a little generous this week, I suppose. So I'm going to just go ahead and jump right into it. Alright, so a lot of these synthesis problems, what I've seen from his exams, he tries to trip you up, he tries to confuse you a little bit with his questions and his wording, and sometimes even and what you'll see later is sometimes the mechanisms look really complex because he gives you really complex looking structures. But I'm gonna show you that it's actually very straightforward. So let's go ahead and get right into it. So this synthesis, we are asked to give two possible synthesis for this ether complex right here. If you didn't know, that is an ether. The ether is always an O bonded to two R groups like this. Okay, so please make sure you know what an ether kind of looks like. Here we're given that this ether is, or we're supposed to provide two syntheses for this ether, and we have to explain which one is better. So we briefly went over the synthesis of ethers, but I think it's best that I go over them again. But with ethers, what you want to do is you can hit an alkyl halide, so any kind of alkyl halide, with an O minus group, so an RO minus group, and you should get your ether. So for example, like if I had BR like this, and I hit it with RO minus, okay, see the minus, just erase that, it's going to get you ROR. So because that bromine is our leaving group, and this O minus tags right there, okay? So that's basically how you form an ether. Very simple, and this runs in an SN2 fashion, okay? Now another way you can form an ether is actually with alcohols. So instead of an RO minus group, I can actually have an ROH group like this, okay? And that will form same product. But the only difference is, you see, compared to the RO minus, the ROH is a neutral compound, so it's not very nucleophilic. It's actually a very weak nucleophile, which is what you need to know for exam, is that if you have an alcohol group, it's usually a weak nucleophile. So if we're working with a weak nucleophile, this is going to be an SN1 mechanism, okay? So the way that works is, the bromine leaves, we get an R positive carbocation, then the nucleophile attacks, we get an ROH like this, okay? Remember the R groups are all alkyl groups. That positive is there, and then what happens is another ROH will invite itself here and actually just snatch away that, and then we form our final product like this, okay? So that's two ways you can form a ether. All right, so I'm gonna go ahead and do this problem. So first thing I want to do is I actually want to draw out this ether because I want to know what carbon pieces that I'm working with. All right, so right now it's given to us in just the molecular formula, but what I want to do is draw it out. So I'm going to draw an O in the middle, okay? And what I see is on the left side, I have a CH3-2CH, okay? So what that looks like is, actually let me draw it a bit better. So let me start drawing it from the carbon. So CH3-2CH. So this, what that looks like on the left side. Notice we have two CH3s right here, and then that's the CH in the middle, okay? And then on the right side, we have a CH2CH3. It's just going to look like this, okay? So that's my ether, all right? Pretty straightforward, not too bad, okay? Oh, sorry. So now that I know what my R groups are, I can go ahead and use the alkyl halide with the strong base, like a RO minus, that will form an ether. So one way I can do it is, let's say I have the O minus on the left side. So let's say O minus on the left side like this. That means my right side should be, that means my right side should be the alkyl halide. So that's what it looks like. And it's going to react to form this product. Okay. Now I could also have the O minus on my left side. So let's say I have Br on the left, and then hit it with O minus like this, and it'll give me the same product, like that, see? And then remember, we also did an SN1 version. So what I could have is, I could have, let's say, the Br like this, plus OH, so an alcohol group, and that should get me, oh, sorry, that right there. Now, first off, we're asked, oh, sorry, there's also one more. We can also have an alcohol on the left side. Forgot about that. So I just drew out 4 possible ways in making a ether. Okay. Now remember, the bottom 2 are SN1, top 2 are SN2. Now going back to my question, I'm asked to explain which synthesis is better. Okay. So off the bat, I know that SN2 reactions are usually better than SN1 because they happen in one step, they're faster, and they're usually stronger. So off the bat, I can go ahead and cross out these 2 on the bottom, these SN1 reactions, because they're not going to react as well. Okay. Reason why is because the nucleophile, in this case the alcohols, are very weak compared to the O minus on the SN2 reactions. So they're not going to be very good, very strong nucleophiles. They're not going to run the reaction in a faster. Okay? In general, SN2 reactions are faster than SN1. So you can say they're better. Okay. So I'm going to go ahead and actually just cross those out. And then between the top 2, this is where I want to go back to my characteristics of SN2. Okay. Now, with an SN2 mechanism, right, usually I want my substrate to be primary, right? But in this case, right, I can't quite go with the top reaction. Reason why is because if you remember your SN2 and E2 characteristics, you know that E2 likes strong, bulky bases. And what I mean by bulky is if it's branched, highly branched. Okay. Now SN2, right? Sorry, that's bad. SN2 likes primary substrates. So I would think the first reaction, number 1, I would think that's better, right? But actually, because my O minus group, in this case, this one right here on the left, because that's actually bulky, it will compete with E2, and what you'll realize is actually E2 is going to be favored. Okay, so you can technically get both products, but E2 is going to be favored, and that is not going to be good for my synthesis. I want a reaction that favors the SN2 product, because why? I'm trying to make an ether product, where I'm trying to synthesize the ether. So you see how that O minus is, that O minus group is bulky. So because it's bulky, it's going to favor E2. That's why if I go to my second reaction, I see that the O minus group is actually not as bulky. So this one is bulky, not bulky. So if it's not bulky, it's going to favor SN2. So because of that reasoning, this reaction right here is going to be the best. And the reason why is because SN2 with a small base means good nucleophile. I'm going to put NUC for short. And so it's going to have little competition with E2. Okay, so I want you guys to understand that if you're going to work with an O minus group, okay, any RO minus group, if your R group is bulky, like in reaction 1, it's going to favor E2 always, okay? If your RO minus group is bulky, it's going to favor E2. That's why I went with the second option, because the RO minus group is not as bulky as the one in the first reaction. So it's going to prefer SN2 in that case, okay? So that's why this one is going to be considered my best one. Actually, let me just circle it. All right. So just to review, we crossed out the bottom two because they're SN1 reactions, and usually SN1 is not as fast as SN2. I mean, SN1 happens in 2 steps, so automatically it's not as fast, whereas SN2 happens in 1 step. And then between 1 and 2, the number 2 is favored, or number 2 is going to happen faster because the O minus group is not as bulky, so it's not going to compete with E2 as much. Okay? All right, good. So now moving forward, we have another synthesis problem. This one is a bit more of a straightforward synthesis problem. All right, we're given a reactant, starting material, and we're also given the product. Now, first thing I want to do is I want to identify what's different between the reactant and product. Okay, so just like the last synthesis we did yesterday. And what I see is that the only difference is that there's a double bond. So I know that I'm going to have to eliminate in one of my steps. And in order to eliminate, I'm going to need a leaving group. And the only reaction I know that will add a leaving group, or a good leaving group, to an alkane structure like the one on the left is Br2 and light. Okay, so starting from this starting material right here, I'm going to need, oh, so sorry. Oh, never mind. I'm just going to leave that there. I'm going to need Br2 and light. And what you'll see is that it's going to add to the more substituted side. Now, it's going to add the bromine right here. Now, I want you guys to pay attention. Do not make the mistake of adding the bromine here, okay? Because you may think that's the more substituted side, but what you'll notice is that that carbon that I highlighted in yellow already has 4 bonds, okay? And it does not have a hydrogen that it can replace with bromine, okay? It already has 4 bonds. All 4 bonds are with carbons. You can't replace a carbon with a bromine, but you can replace a hydrogen with a bromine. So don't get confused there. That's not the more substituted side. This side, the one in green, is going to be the more sub side because that has 1 hydrogen that can be replaced with the bromine. Okay, so don't make that mistake. Now, I need to get to the elimination product. So I have bromine, and it turns out the bromine's in a perfectly good position to eliminate, so I can get my double bond in that area. Now I just need a good eliminating group, or a good strong base that can eliminate. And I want you guys to remember this reagent called tert butoxide. Okay, it's gonna look, you can draw it out like this, and also make sure you put K plus 2, okay, because it exists in a ionic solution. But this is tert butoxide, okay? You can also write it like this, and you can also write it like this. All of them are acceptable, okay? T-bu is just short for tert butyl, okay? But I'm just gonna keep it like this. And this always goes E2. Always E2. Why? Because it's a strong, extremely bulky base. Okay? It's a strong, bulky base. So it's always going to go E2. So what you're going to see is that Br is going to get eliminated, that double bond forms. And boom, we have our final product. Look at that. Pretty simple. So if you ever need a leaving group to be added on to an alkane structure, use Br2 in light. And if you never need to eliminate something, use this tert butoxide, okay? Now moving on to the next problem. We have another synthesis. This one, I'm actually going to start from the product and work my way back to the reactant. So there's different methods you can use for synthesis. You can do what I did earlier and start from the starting material, then get to the product. But some people like to do it from the product to the reactant in what's called a retrosynthesis, because you're going backwards technically. Now, if I'm going to do that, I want to identify what's different between my product and reactant. What I notice is there's a double bond here in green, and then there's this OH group. Now, another thing I want to notice is I want to notice the positions of these groups. So the double bond in green, right, is adjacent to the OH. Now, from my knowledge, I know that NBS in light adds a bromine to an allylic position. Allylic meaning that it's adjacent to the double bond. So this carbon right here that it's highlighted in red, that's adjacent to the double bond. So that means it's allylic. And there is one reagent I know that adds a bromine to an allylic position. That's called NBS in light. Good job. And then from there, all I need to do is substitute that bromine for the OH. But before we do all that, I need to get a double bond on there. So we're actually going to do the same step we did earlier from here, and we're just going to do Br2 in light and then eliminate that. So I kind of have an idea already, but first things first, if I know I need a bromine in that allylic position, I know that my structure is going to look like this. Okay, so I'm going backwards. I have the bromine there instead of the OH. Now I need to figure out what will substitute that bromine with OH. And what I want you guys to use is NaOH. Okay, that will do an SN2 substitution, and it's very straightforward. Now I know what is going to make that bromine NBS with light. Okay. By the way, you can write light out like this, or you can write HV if you want for NBS. But if you're using Br2, I think always use HV. Okay. Now, why would Br2 in light not work here is because Br2 in light only adds 2 alkanes, right? And NBS in light adds bromine to the allylic carbon, that is the carbon adjacent to a double bond, okay? So what is that going to look like before. It's going to just look like the double bond, like this. Look at that. Now, I know I need something that will eliminate a leaving group to form the double bond. But first I need to figure out how to get a leaving group on there. So let's say I have bromine on that carbon. I can eliminate that bromine with terbutoxide. Yes, good job. Now how do I go from the cyclohexane to the bromine one? All I need is Br2 and light. So that's how you go from the product to reactant. Now if you want to go back and check your work, I think you should go back and check your work, absolutely, but start from the reactant. You're going from cyclohexane to the bromocyclohexane. Br2 and light does that, so that checks out. Then I want to eliminate that bromine. I use terbutoxide, checks out. I want a bromine on allylic carbon, so I use NBS and light, checks out. Then I want to substitute that bromine with an OH. I use a strong nucleophile like NaOH, checks out. All right, not too bad. So moving on, now we're going to get into some mechanism, okay? Now remember in class what I told you that when you're doing a mechanism and you're given the product, you want to always identify what kind of product is being formed, okay? So in this case, what I see is that there's definitely a substitution going on because that bromine is gone and it's replaced with an OCH3. But what I notice is that that OCH3 is being added to the opposite side. It's being added to where that double bond is. So I know there's going to be some rearrangements, okay? And what I notice from my nucleophile, which is CH3OH, that's a weak nucleophile. So I know it has to be SN1E1, okay? So what I'm going to tell you right now is that your mechanisms on your exam are going to always be SN1E1, okay? And the first step of every SN1 and E1 mechanism is that your leaving group is going to leave, okay? That is going to form a carbocation right here, okay? Now, what I notice from my product is that the OCH3 is actually on this carbon right here, okay? So that is going to be this carbon right here on the reactant. So I know there's some rearrangement going on here, and the rearrangement actually is fairly simple. So another thing that I notice is that the double bond ends up in the ring. Okay, right now it's outside the ring, but it's going to end up in the ring. So I know that I need to move my double bond into the ring. But in order to move a double bond, I need a positive charge on the adjacent carbon to it. Right now, on this carbon right here, there is no positive charge. Let me actually circle it. On this carbon right here in green, that I just circled, actually let me circle it in blue. This carbon right here that I circled in blue has no positive charge. So I need to get a positive charge on there. So what I can do, actually move this positive charge from the other carbon via a hydride shift. So you see how there's a hydrogen there? I can do a hydride shift, okay? This is one of the rearrangements that you need to know. And that's going to form, that's going to put the positive charge on the top. And that hydrogen moves here, which is exactly where I want that positive charge to be, okay? Next, what you'll see is I can now move the double bond over, all right? But what I want you guys to realize is this is resonance, okay? So that double bond is able to resonate with the positive charge. So if you're showing a resonance form, always show an arrow like this with a front arrow and a back arrow like that, and then show the final product this. what you see is that positive charge ends up on the outside carbon. Okay. And then another thing you need to show is that you need to always put brackets around the resonance structure. So these are resonance. So resonance is when electrons within the molecule are just moving around and shifting. So nothing is being attacked, nothing is being removed. All that's happening is that the electrons are shifting in the structure. And I'll also keep that H there just so you guys can see. So if you're showing the electrons moving within the molecule, okay, showing a resonance structure, you need to put it in brackets. You need to use arrows like this, okay, right here. And you need to show, the brackets, okay. Now we have our positive charge where we want it to be. So our nucleophile, in this case the CH3OH, is able to attack. And so what we end up getting is, sorry, let me move some stuff down so I can get some more space. That was kind of awkward here, but now that we have that, we can have our nucleophile attacking. So we see is an O, is an H, is a CH3. What am I missing? That positive charge. Good job. And how do I get rid of that positive charge? Well, I'm going to need another nucleophile. Snatch the H away. This bond breaks. Goes over here. And that's how we get our final product. Okay? So, pretty straightforward. Not too bad, right? Yeah. So, notice the rearrangement. Notice that we have to use resonance here in order to get the positive charge to where we need to be. Okay? Remember, for resonance, you're always conserving the charge in the molecule. So you see how between these two resonance structures, right here, between these two, the overall charge is the same. Both are positive, but just the position of the charge is different, right? So I wanted that positive charge to be here. I wanted that positive charge to be here so I can attach my OCS3 there, okay? All right. Moving on. Now this looks really, really bad, I know, but I am going to tell you right now, it's actually very, very straightforward. So first thing I want you guys to notice is that the reactant, right, the starting material, there's a cyclohexane structure in the middle, right here. There's a bunch of triangles, right, all around, okay, a bunch of cyclopropanes. The final product still has the cyclohexane structure, so nothing's happening there, but we're forming squares now. See that? So we're forming cyclobutanes. So I know that there's definitely some rearrangement happening here. Okay. Now, in order for rearrangement to occur, I need a positive charge. I need a carbocation. So what you'll see is we can actually make that carbocation by protonating that water. Okay. So you see how the H plus right here, that indicates that the reaction is happening in acidic conditions. And right here we have an OH. Okay, this OH right here. What's going to happen is that OH is going to get protonated. So it's going to attack the H plus. What you see is that it'll eventually, well, not eventually, but it'll just form water. So if I just draw my CH3 like this, it's going to form water. Make sure you always show the charge on top. Then drawing my triangles. It's a very messy drawing, but forgive me, I'm a little tired. But yeah, now we have the water, and now we've turned that OH into a good leaving group. So now it's going to leave. So you're starting with OH, you're hitting it with an acid, it's going to protonate, become water. That water is now a very good leaving group, so it's going to just dip. It's going to just leave. And so we end up getting the carbocation that we were wanting. So the carbocation is going to be on the top like this. CH3 still there. And then we form the triangles. This is going to be kind of annoying to draw, but or fun. If you think this is fun to draw, then I don't know what's wrong with you, but sure. Now this is where the rearrangements come in. So what you're going to see is that when it comes to rearrangements like these, all you're doing is you're just breaking a bond and reforming a bond somewhere else. Okay. Now I'm going to go ahead and start on this right hand side. Okay. Actually, first let me go to the product. So what I see here is the triangles are becoming squares. Okay. So I know that this bond has to, down here. This bond has to break. What's happening is a new bond is being formed here. Okay. So we break this bond. Okay. Break it apart. And then we form a new bond with that carbocation. Okay. See that? So the way we show that, if I just erase everything out, is we draw an arrow going from that carbon to the carbocation, and that's going to be our first rearrangement. And we actually end up forming a square right there. Okay, so you see how we did that? So the triangles become a square. Now we need to decide where that carbocation goes, because remember, all we're doing right now is doing rearrangements, but the charge is still there somewhere in the molecule. Okay, so now we had to think about it. So let's look at this carbon right here, carbon A, and this carbon right here, carbon B. Okay, so what we did is we just pick a different color. We broke this bond between that carbon and carbon B, and we formed a new bond with carbon A. Okay, so we know that carbon A has to be this one, right? Because carbon A has the methyl group. This one has the methyl group as well, so that has to be carbon A. That means this one has to be carbon B right here. And what we realize is carbon B initially had 4 bonds. Okay. But after we've broken this bond right here, after we've broken this bond, it now only has 3 bonds. So it's going from 4 bonds to 3, so it's losing a bond. That means the charge has to be a carbon B. You see that? Now what you realize is you can just do the same thing all the way around the ring. So we show that moving there. And we can show another structure, this. And then we can actually draw another square here, which realizes that carbon on the other side gets the charge via the same pattern. Okay, see here, say we call this carbon C in blue. This is carbon C now. It goes from 4 bonds to 3, so that's how it gains the positive charge. And then we do the same thing all the way around. So arrow there, we get this one here. These two tough triangles. This has a square, this has a square, and now we have another square right here. The positive charge ends up here. Arrow again. I'm going to go down. another square, positive charge ends up here. Boom, another arrow, and that should be the final rearrangement we have to do. I think, yeah. So now we have these squares all the way around. Look at that. And that positive charge ends up here. Okay, and then there's a methyl still there. Now we're not quite done yet, because our final product, that OH returns. And so remember, in the first step, we made water. So that water is going to make a return. Okay, the comeback water. Water is going to return. Water that we made in the first step will attack that positive charge. Oh, sorry, let me draw it going down, so I don't want to take up space. I gotta draw every single one. And then we have water back here. That positive charge is going to end up on this. Okay. Now we got to somehow deprotonate this water. What we're going to do is the entire reaction happens in water as well. So it's going to snatch H. This happens. That, by the way, is a very common thing that's going to happen in the mechanisms. You're going to deprotonate water or protonate OH to make water. Okay. And with these mechanisms, you can react water as many times as you need to get your final product. And then I didn't draw in stereochemistry for the sake of like time, but at the end you can show that these boxes are on a wedge, like so, and these boxes are on a dash, so. And let's do that all the way around until you get this product. Okay, not so bad, right? Okay, good. So good luck tomorrow. Love you guys. Yeah, peace.